So first off, I didn't even read our objective for today, for 8.1. Be sure you write this down in your notes. We're always going to have an objective. The purpose of today is to graph exponential growth functions. We're also going to look at interest problems because they deal with exponential growth. So the second piece is the warm-up. When we describe end behavior for each graph as x approaches positive infinity, I'm going to go about this in a different sense. Most of you chose to go plug in a number, and if I end up bigger, then it's positive infinity. We realize this one's getting to positive infinity, but I'm going to go about it looking at degrees. The degree of this polynomial was cubed, and last semester we talked about how the shape of a cubic function looks a little disco. And if I'm talking about as x approaches positive infinity, we said this means goes to the right, or the right arrow. So if I look at the right arrow in this graph, it's approaching positive infinity. The way we write that is f of x approaches positive infinity. The next graph, I notice the degree is cubic. The bad thing is, I also know that the leading coefficient's negative. When the leading coefficient's negative, it reflects, or it switches, flips, some word. It flips the original degree. I look at the right arrow, and hopefully when you plugged in your really, really big number, you should have gotten a really, really negative number. So f of x is approaching negative infinity. Last one, x squared. So if I look at the graph, is a parabola in this last one. And if I'm looking at the right arrow, it's also pointing up. So if you plugged in a really big positive number and you got even more positive number, the end behavior is approaching positive infinity. We're going to start off with the definition of an exponential function. An exponential function involves the expression b to the x, where b, or base b, is a positive number other than 1. In your notes, there's a typo here. It says other and, my bad, other than 1. The way we're going to go about this is we're going to plug in my 7 common numbers that I like to do. So I'm going to plug in -3, -2, -1, 0, 1, 2, 3 to get a general sense of what's going on here. So after we plug them in, let's start graphing them. There's something special that happens. After exponential growth, well, it's going to grow. It's going to grow really fast. But we've got to figure out, well, what's happening down here? Am I going to cross the x-axis? What happens? So let's actually plug in. I'm going to ask one more person to plug in -10. And I'm going to graph that point as well. So that's really, really close to 0. And then I'm going to connect my points. We need to notice that this graph actually never, technically it's not supposed to touch the x-axis. This point 00098 is not on the x-axis. It's close, but not on it. We call this an asymptote when you get really, really close to a number and you slope off. That's where this asymptote, it's a line that a graph approaches as you move away from the origin. This line is technically where the y-coordinates, notice these y-coordinates are getting closer and closer to 0. So the asymptote would be y equals 0. Let's go back to end behavior just a little bit. So, since that was part of warm-up, I'm going to just add this to the graph. As we go to the right, so as x approaches positive infinity, Well, the right arrow is pointing up, so f of x is going up. But let's talk about as we go left. As x approaches negative infinity, we actually don't have a down arrow. We have a left arrow. So this arrow is approaching 0. When we have an asymptote, then the end behavior actually approaches that number. This is the first time we're actually seeing a number and not an infinity. So characteristics. First off, if a is positive, if this leading coefficient is positive and the base is bigger than 1, this function, y equals a times b to the x, is an exponential growth function. So exponential growth function. So if you have a base that's bigger than 1 and the a is positive, you have an exponential growth function. And there's certain types of characteristics, but these characteristics only deal with if it's in this form. If there's anything else going on in the exponent, or if there's like a +1 hanging out here, then the rules change. So in general, if we have this piece, y-intercept is a, the leading coefficient. The x-axis is actually the asymptote of the graph. Sometimes we want a specific line equation, and in the previous example we had y equals 0. Domain is all real numbers. You can plug anything into that. And then let's talk about range. Range, notice how the range changes. The range isn't all real numbers. The range will be y is bigger than 0 if your leading coefficient's positive. It'll look like this if your leading coefficient's negative. So this is what we'll write down for the range depending on the leading coefficient. All right. So let's graph. Here we go with graphing. First example. So with this, let's plug in, my suggestion when we graph these is we're going to want to know what happens at the extreme, that -10 that I made somebody answer, and then let's just go normal, 0, 1, 2, 3. First off, notice some characteristics. Notice how we slope off here. This sloping off where we get a flat line, this is called an asymptote. In every single one of these graphs, this chapter, we're going to deal with an asymptote. We've just got to figure out, okay, what is it approaching? Notice how the y-intercept actually came out to be this coefficient. So it's another way to check, but this is a plain Jane equation. That's how this turned out. Okay, so domain. Got to figure out domain. So here we go. You're looking at that characteristics box. All real numbers. So because the 2/3 is positive, the range, y is bigger than 0. And notice all of our points, too. All of our y coordinates didn't turn out. They all turned out to be positive. So it's another way to check. We're going to do the same T chart, where we're going to plug in -10, 0, 1, 2, 3. -10 helps us figure out where's that asymptote. 0, 1, 2, 3 help us figure out, okay, what's the rest of this graph looking like? So exponent first, -10 plus 2. My bad, not plus 2, it should be -2. Take 3 to that power, multiply by 2, and then add 1. So we get the following points and we graph them. So let's talk about this. The previous graph only had 2 times something to a power. or it was 2/3 times 2 to a power. There was no -2 in the exponent, no +1 hanging out up here. And both of these pieces are shifts. We've got a horizontal shift and a vertical shift. So that means some things are going to change in this answer. But something that always stays the same is our domain answer. Domain! So in the range, not approaching 0 anymore. So it's no longer y being bigger than 0. You've got to realize, wait, what are our y coordinates approaching? So because our asymptote's approaching 1, our range changes also. Our y coordinates are just bigger than 1. So first off, when a quantity increases by a fixed percent each year, by the way, this fixed percent is our rate. So what I need to do is draw an arrow from R. This is the percent increased, but it's always going to be written as a decimal. Or we will need to write it as a decimal. It should not be in the percent form. And let me be clear about this. It's going to be in the percent form in the words, but you're going to change it to the decimal when you plug it into this problem. A is your original amount. Because in order to build up interest in a bank, you have to have some type of an amount in the bank. T is the amount of years. In this problem, so reading through it, in 1990, cost of tuition at a state university was $4,300. After 1990, the tuition rose 4% each year, which typically happens. Write a model that gives the tuition Y in dollars T years after 1990. So here's what this last statement means. Writing a model means I need an equation, and in my equation, I need a variable Y and a variable T. So already, this is going to be my equation right here. Whoopsies, I forgot a placement. There should be something written here as well. But there's going to be something in my A spot and in my R spot. So rereading the problem, because 1990 deals with time, and wait a second, I want a model with T, I'm not going to use 1990. So again, this last statement will tell you what variables are going to stay. Cost of tuition was $4,300. This is your original amount. I'm going to put that in front. That 4% is kind of a dead giveaway. This is your rate. But I don't want it as a 4 here. I need it as a decimal. 0.04. Because in the inside here, 1 plus 0.04 can be simplified. Let's actually write it a little bit nicer. Our equation will be y equals 4,300 times 1.04 raised to the t power. Using this equation, we're going to figure out the cost of tuition in 1998. Notice how in this model it says T years after 1990. So how many years after 1990 is 1998? By the way, this question is not in your notes. You need to write it if you haven't done so already. So, after the discussion, T years after 1990, 1998 is 8 years after 1990. So, when we plug in T, it's just going to be an 8, not 1998. So this is the tuition in 1998 after it rises, tuition rising 4% each year. So compound interest, you might want to underline that word or those words. compound interest. You're going to have a problem in your homework that says, using compound interest, blah, 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 this is the equation you need to use. A equals P times the quantity, 1 plus R over N, all raised to the NT. And we're going to write in these spots what each of those mean. Here's what I mean by number of compoundings in a year. You're going to see this is compounded quarterly. Well, quarterly means you're doing 4 times a year. So 4 would be your N. You might see compounded monthly, which is actually typical if you use a bank, compounding monthly. So monthly would be 12 times in a year. You deposit $1,500 in an account that pays 6% annual interest. Find the balance after 1 year if the interest is compounded each one of these options. So we're going to start with A. In this equation, this y equals, y was the last one. A equals P times 1 plus R over N to the NT. So wait a second, what's P? What do you start with? And we're starting with this 1,500. So instead of P, I'm now going to have 1,500 in its place. And then the rate is pretty easy to pick out. I just have to write it as a decimal. I then find the balance after 1 year. Anytime I see year, this is dealing with our T. So in place of T, I'm putting a 1. I'm actually going to use this format for every problem. It's the N that's always going to change. Annually, how many times a year would this be compounded if it was annual? So instead of N, here's how we compute this problem. I have to do a few things before. I can't just compute it all at once. Maybe I can do some of this in my head, like 0.06 divided by 1 is just 0.06. This exponent, 1 times 1, I just have an exponent of 1. So maybe in my calculator, I'll put 1,500, open parentheses, 1 plus 0.06. Some of you could do that addition in your head. Raised to the first power. And maybe we don't need to raise it to the first power, because it's compounded semi-annually. So semi meaning 2 twice a year. So now our N is going to be 2. So this red is going to change to be a 2. Everything else stays the same. The red's going to be a 2. So now this amount changes to 4. And this also shouldn't be too different. It's like 1,592.05. Notice how the problems say 55 ABD. 55 ABD. Don't do C.